I don't know who's absent. So this is based on a true story. Many years ago, back in the late 1700s, there was this little fella named Freddie. His actual name was Frederick Carl Goss, but little Freddie was one of those students that teachers love and hate to have all at the same time. So little Freddie was a little wee tyke, and he was in early elementary, right around first grade, if they called them grades. And he was one of those kids that no matter what you gave them, they did it in 3 seconds, and then they were disruptive, annoying, kind of a show-off. You know, ones that kind of, yes, that send the class in the wrong direction. So little Freddie's teacher had enough. And the teacher told little Freddie, it's fine, go back to your desk and add up the numbers 1 to 100. Okay, so little Freddie's like 6 or 7. This should take a while. Because a lot of kids that age struggle to count to 100. So I'm not sure if the instructor was female or male, but they thought this should give me at least 10 minutes. Unfortunately, little Freddie came back in less than a minute with the answer. All right. So what did little Freddie do?
He used the arithmetic sequence.
How did little Freddie do this?
Nobody.
Well, this is what little Freddie shared with the world. And little Freddie turned out to be Frederick Douglass was another very important person in history. But Frederick Carl Goss. And if you study mathematicians, you can, because I'm sure all of you will move on to study mathematicians.
So this guy's like the best person in math like ever.
He actually ended up contributing much to the field of math. Ooh, Goss. This Goss has 2 S's. So he actually lived from 1777 to 1855. So we know that little Freddie didn't go back to his desk and pull out a calculator to do this. So what did little Freddie do to find the sum accurately in less than a minute? All right, so little Freddie was a thinker. And I have students that are thinkers. I get 1 or 2 every couple of years that just like to think about things. And it's pretty cool. I've got one right now. Yesterday we had math team, and in the middle of math team yesterday, one of my students that enjoys thinking about things looked to me and said, Miss Willoughby, what are your thoughts on the commutative property as it pertains to omega?
What?
Wow. Wow.
And I went,
That was just like.
so what are you talking about? Because we weren't talking about the commutative property as it pertains to omega. And he goes, do you feel that 1 plus omega is the same as omega plus 1? And I was like, I'll have to get back to you on that. Honestly, because I had no clue what he was talking about. So I had to go do a little research so that I could have this discussion with him. He goes, I was thinking about it, and so I started researching it. And then this guy wrote this book about it. He goes, so I ordered the book. I'm like, well, good. When it comes, share with me what you've learned. So there are some people that just enjoy thinking, finding quicker, better. There are people, and some of you may enjoy it, maybe not in the field of mathematics, but you might enjoy thinking about other things. Well, Freddie was one that liked to think about mathematics. And this seemed like a mundane problem to little Freddie. So what he did was this. He thought, what would happen if I lined it up this way? And he saw an interesting thing occurring. What if instead of doing 1 to 100, I did 100 down to 1? But then when he wrote that, he looked at it and went, oh, well, this is neat. Because if I were to just add these 2 up, look what I get. 101, and then 101, and then 101, and then I get 101, and then he was done. He had the answer to the problem.
Hold your horses.
Okay.
Like, what?
Because he gets 101 100 times. 100 times he gets 101. Because there were 100 numbers, right?
How old was Freddie?
Bruh.
He was early elementary.
Oh my God, this kid's
Yeah,
a genius.
yeah, he was. Okay,
Literally gotta do
but
that.
Freddie had a problem.
It's fake.
His teacher only asked him to add, Zach, here was Freddie's problem. His teacher only asked him to add 1 to 100. Not 1 to 100 and then again from 100 to 1.
5 by 2.
So he had to divide by 2.
Alrighty, let's,
Alright, so Freddie immediately said,
I don't think so, but there's some thinkers.
it is 50-50.
I don't think he did it under a minute.
Sounds bad.
No, sure.
Yeah, he did.
No, he didn't.
Well, you know,
wait, but 50 plus 50 is 100.
You think this man did this?
you are correct.
Whoa!
You got another thinker.
Falcons book 28-3 lead, yo.
Alright, so,
Wait.
how does this have anything to do with what we're doing today?
It doesn't.
It has everything to do with what we're doing today. Because what we're doing today is finding the sum of arithmetic sequences. And that's called a series.
But what happens
So-
when you get to 50 and 50? Like you go 5 all the way to 15?
50 doesn't line up with 50.
50 lines up with 51, Chase.
Yeah.
Duh.
Oh.
Shouldn't you think about that first?
Actually, there's another way to think about it, and he may be there.
Fingers.
I'm not there.
No, he's not.
There is another way to think about it. Averaging them gets you to 50. And how many times do you get 50?
201.
101. Because, yeah, if we thought about it that way, if we, instead of, I'm with you. You can think about it this way too, and you have this extra 100 out here, and you pair these two, and you pair these two, and you pair these two.
It's 100.
It's the same kind of idea. But there's 51 of them because there's this extra. Anyway, all right. So a series is a sum where we add up the terms of a sequence. Okay? Now, this Greek symbol is not only found on fraternity row in colleges. It is also found on math worksheets. This Greek symbol in mathematics means summation. Okay? This is not just sigma whatever. It is summation in mathematics. So if you see this crazy symbol, it's easy. Unless you don't know what it means. And then it's impossible because you don't know what it means. So this symbol means to add up, to find the sum. That's all it means. Okay, so we have already studied arithmetic sequences. And yesterday we revisited that formula that we use for a sequence. Now, how can we take what little Freddie did and apply it to anything? Okay? So here is the proof. Some of you guys like to know why. Why does this work? This proves why this works. Okay, a sub 1 represents the first term. Are you with me? Okay, so to get to the second term, don't we just add a common difference? So a sub 1 plus d would represent the second term. So to get to the next term, would I just add another common difference? So my third term would be a sub 1 plus 2d. Okay? My fourth term would be what? You tell me. Yes, it is. Okay. And this works all the way, dot, 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 I'm not going to write them all, until we get to the end. And what we use to represent the last term, we call it the nth term. That's what we use to represent the last term. Well, to find the nth term, we already did this. To find the nth term, we do a sub 1 plus n minus 1 times d, or d times n minus 1. You could write it either way. That's the last term. Are you with me? Okay, so let's use Freddie's logic. So let's take this and work our way backwards. So if we took this one and added it right here. A sub 1 plus D times n minus 1. And then we did, I'm just going to put the big pluses in here, so in a different color. All right, so this one is the term before n minus 1. The term before n minus 1 I could represent as n minus 2. Does that make sense? And the term before this one would be n minus 3. And the term before this one would be n minus 4. All the way until I got back to the very first term. And what represents the very first term? A of 1. Okay, so little Goss would have taken it this way and said this and this together would be 2 A1s plus D times n minus 1. And in this plus this, okay, do you see when I distribute this D right here? It's negative 2D. But if I add a D to it, it's negative 1D. This is negative 2, but if I add 1, it's just negative 1. And then this one turns into 2A plus D times n minus 1. And this one turns into 2A plus D times n minus 1. All the way until we get to this, which is still 2A plus D times n minus 1. Every time. Every time. But the problem is, we doubled it. We doubled it. So we have to take however many we did and divide by 2. Because we doubled it, we take the number of terms and divide by 2. So this is the formula, folks.
Wow. Slow.
Okay. Now, you're looking at your notes going, Miss Wilby, that is not the formula that's on the notes. It is. Watch this. If we take this A and split it back, oh, you're going to love this.
So is this what we do for each problem?
No, no. This is how you learn.
She's just explaining how the formula works. Yeah, this is not how we do it. So you can do this. I don't care if you do it, but you can.
All right. So if I took that A and split it back, guys, do you see what this is?
Same stuff.
This is A sub n. This is A sub n. So here is the formula that's on your sheet. It says do the first one plus the last one times n over 2. Okay. I am not going to ask you to prove it like I did, but I am going to ask you to use it. And I did want you to know where it came from instead of just me saying, hey guys, memorize this. Okay? So, this is what it is, and this is how it was developed. This is the formula we'll be using. And that is where it came from. Okay, there's one person that's thinking about it, and I'm waiting for that aha moment to happen, and then I'm going to flip the page.
It's the same thing.
Yeah.
with the-
It's not gonna get to me.
Oh, it'll happen. We'll talk through it just a second. It's going to happen.
That means if she doesn't understand it, then I don't have to understand it either.
Actually, she had several aha moments in the example, so she's going to be just fine. She'll be just fine. All right, so do you see that this is the formula?
Karen, you got it?
Okay.
And that this is a variation of that formula. So if you know the last term, you're using this. If you don't know the last term, you have to do this to find the last term and plug it in. Which means you could just use that formula. Because this formula is these two put together. This right here is just those two put together.
Go ahead, write that down.
No.
Okay, so add this to your notes. Now the little story I told you about little Freddie,
That's fake.
it may be like one of those
It's a folk tale.
folk tales,
Oh my.
but
goodness.
it has been passed down in history as something that actually happened. But it could have been something, you know how like old men tell stories about when they were young? He could have just made it up. But if you do research Frederick Holocaust, you will see he actually has made many contributions to the
So
field.
you just tried to hook us. That was your hook? You're in
No,
for a
if you
rap.
research it, it really is it really
No,
is
like
a
the
folk
first
tale.
grade thing.
No, it's actually part of the folk tale. You can look it up.
That's the
Now,
hook.
I can't prove the reality of that because I wasn't in his class back in 1782.
You think you
That's
can take
what I'm trying to
No,
say.
no,
Oh,
so
that's
it's not math. Alright, so that sequence is just a list of numbers. An arithmetic sequence is that list of numbers that has a constant difference. We actually have two types of sequences. We have a finite arithmetic sequence, and we have another type, infinite. So what do you think we mean by finite versus infinite? Finite finishes, infinite does not. Okay?
Holy.
I like that. I usually say that finite has an end, and infinite does not end. But I like it. Finite finishes. Okay, so here we have three sequences. It asks us to identify or label them as either finite sequences or infinite. Now with the infinite, what we're looking for here, infinite doesn't end. So what it's going to have is the dot, 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 the ellipses, to let us know it goes on forever. And there'll be nothing at the end of that. So obviously this one has no ellipses, so it is finite. If it's finite, we can always determine the number of terms. In this case, we can count 6. That was nice. All right, this one has my little ellipses, dot, dot, dot. Goes on forever. There's nothing at the end of it. This one's infinite. So we can't count the number of terms because it never ends. All right, now this one has the dot, 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 but look what's at the end of it. Our ending number. So this one, even though it has these ellipses in here, is actually finite. Now, I have a problem though. I see 4, 5 terms, but I don't know how many are in between here. So how can I find the number of terms? Well, I can go back to the formula we had yesterday. We know the last term is 94. We know the first term is 4. And we know the common difference is 3. Then you can solve for n. So this first formula is a very important one. All right, so I would subtract 4. I would divide by 3. And I would find that there are 31 terms in that sequence when I add the 1 to both sides.
Can't you kind of go making a chart calculator? and
That's
tell me
impressive.
that- Make a chart.
For real.
I'm not sure what you're saying.
Oh.
Alright, the next question asks, which type of sequence, finite or infinite, do you think you could find the sum of?
Finite.
And how would we do that? We would just add up all the terms. If it didn't end, we'd never get to the end. Now, when we do add up all those terms, when we do find the sum, we call it a series. And number 1 would look a little different if we wrote it as a series. It would look like this. 13 plus 11 plus 9 plus 7. We would actually put the sum in there. Got it? That's how you know you're talking about a series, when you add them up. They'll either be the pluses or minuses in there. All right. Now, here's our 1, 2, and 3 we just said. Let's find the sum of those finite ones. So, for number 1, honestly, if I had a calculator sitting on my desk and I didn't have a formula handy, I'm probably just going to punch this in. I'm probably just going to add it up. I might try to pair it up to where it's easier for me and go like 12 plus 12 is 24, and 24 and 24 is 48. That's probably what I do. But we actually can use that formula. The sum of a finite number of terms is n over 2, the first plus the last. So in this case, the sum of the first 6 terms is 6 over 2, the first plus the last. And 16 times 3 is the same thing I got a second ago, 48.
That's what I was trying to do. That's what I did at first. It's a lot longer.
Yeah.
You got the.
It works.
That's what I did. That's
It
what I
works.
did.
Cool. Alright, so number 2, we're not going to be able to find this sum because it's infinite. But number 3, we can. So, adding them up by hand is not bad when there's only like 5 or 6 terms. But once we get to like 31, you want the formula. It would take too long the other way. So the sum of the first 31 terms would be n divided by 2. The number of terms is 31 divided by 2. The first term is 4, and the last term is 94. Now, if I had to do this without a calculator, I would take half of the 98 and do 31 times 49. And if I really had to do it without a calculator, I'd probably do 31 times 50 minus 1, because that's easier for my brain to do than 31 times 49. It's easy to distribute that, right? So that's 1550 minus 31. So I'll get 1519 on your calculators.
But where'd you get the -1?
I said if I had to do this without a calculator, I would break the 49.
You divided by 2. Divide.
I divided the 2 into 98 to get the 49.
Okay.
Yeah.
It was really good.
Yeah.
You would say you're pretty skilled with that multiplication, right?
Sometimes. Not if you say things out loud though. I have to see them.
Okay, I thought that you were random.
No, I can't do anything. I'm not an auditory learner. Yeah.
That one math magician. He
Yeah.
goes 6 figures times 6 figures
Yeah,
and does
and he can
it.
do it in his head without saying it. I can't do that.
They use his method is using numbers and words like.
Yeah. Yeah, I've watched those videos trying
Do
to
you
do
think
it
he actually
myself.
puts them into words, or do you think he's just making it a part of the show?
I think he assigns letters for some of them, yeah.
Well, I
But
feel like he's saying that, but while he's saying that, he's buying himself time to come up with the numbers.
Maybe he is. I don't know.
That's hard
do
because
it.
his brain's processing.
Yeah. Alright, so let's do these 3 examples. Find the sum of the first 15 terms, so we know n is 15, and an arithmetic series, so we know we're adding them up. If the first term, so a sub 1 is 10, and the common difference is 4, so d is 4. So, if we use that formula, S of n equals n over 2, the first plus the last, we have to figure out what the last is. And on many problems, you'll have to start with that, determining the last term. So in this case, the last term would be that 15th term. So the 15th term is the first term plus n minus 1 times the common difference.
What's the other A1 plus?
Yeah, is that A of N or N of N?
That should be A. The baby's struggling right now.
It's okay.
All right, so 10 plus 56 is 66. So the 15th term is 66. So the sum of the first 15 terms would be 15 divided by 2. The first term is 10. And the last term we just solved for is 66. And punch that in your calculator, folks. So the sum of the first 15 is, did you get 570? Okay, so number 2 is set up a little differently. We can tell from this series that our first term is 100, our last term is negative 20. We can also see a common difference of negative 5, but what we don't know is n. We don't know how many terms there are. So when we're missing one of these pieces of information, we have to go back to that first formula. A sub n equals A sub 1 plus n minus 1 times d. So we know the last term is 100. The first term is, let me try that again. The first term is 100. The last term is negative 20. And the common difference is negative 5. So we would subtract 100, divide by negative 5, and add 1. Okay, so now we figured out our missing piece of information, 25.
25 is in.
All right, so to find the sum, we have the first one, we have the last one, and we know n. So the sum of the first 25 terms is 25 divided by 2, the first plus the last. Can I get 1,000? Cool. Okay, so a lot of these problems are two-steppers. All right, last problem. Last example is a word problem. So an architect designs a theater with 15 seats in the first row. I'm kind of visual, so I'm going to put 15 seats in the first row, 18 seats in the second row, so it's a little bigger. 21 seats in the next row. Okay, and it just keeps going. And it has 40 rows. So this is our first,
It's like an amphitheater.
second, third, and we come all the way down here, and somewhere way down here is our 40th row.
So,
Okay? But we don't know how many seats are in that row. It didn't tell us, did it? So if we're trying to find the total number of seats, we want to know the sum. The sum of the first 40 rows. So we know it's 40 over 2, the first row, plus the last row, which we don't know.
okay.
How do we find the last row?
Probably another
Plug it
step.
in that other formula.
Yep, there's another
A sub n equals A sub 1 plus n minus 1 times d.
So we don't know A40.
So this is what we don't know. A sub n, A of 40. You're right. So we know the first one had 15. We know we're doing 40 rows. What's the common difference?
30.
3. So that 40th row, gotta do our calculations.
130.
This would be 120,
Yeah.
132.
Plug it in.
So then we can come back up here. The sum of the first 40 is 40 divided by 2, which is 20. 15 plus 132. And this theater holds or has 2,940 seats.
Dang.
Globe theater.
Okay,
Wait,
so the back of this has your practice problems for homework. Let's go ahead and get started.
You're like my favorite teacher this year, but I wish you like teach like something easy, like English or something.